So at the end of the last lesson, I'd mentioned the fact that reactive streams is a little bit more conducive to mapping onto the reactive programming paradigm than completable futures plus Java streams. And so what we're going to do in this particular part of the lesson is we're going to step back and evaluate all the different Java programming paradigms in order to understand what types of capabilities they provide and which ones are truly reactive and which ones are sort of faux reactive. So let's take a look at that, and this will give us a chance to compare and contrast the different approaches. And we'll also talk about the pros and cons of using reactive streams. As I always like to say, not everything is unicorns and rainbows. So there are some downsides to using reactive streams, even though they do have a lot of benefits as well. So here's a diagram that will allow us to do an apples-to-apples comparison between different programming paradigms in Java. And the axes on this fourfold table are whether or not the focus is on synchronous or asynchronous programming, and whether or not the paradigm or the approach focuses on single-valued results versus multiple-value results. So those are the two dimensions. And then across that, I've shown how various paradigms map onto it. So let's start out with your grandparents' Java from 1995 for the next, let's see, 1995 to 2014, about 20 years. About 20 years of Java. Mostly what we had were synchronous style communication, with a few exceptions, like the executor completion service, but most things were done synchronously, and most of the processing returned a single value. And here's a very good example of this. This is an example where we're going to download some content at a given URL and return a byte array. And as you can see, this would be something that would be a method in an object. You could call that on some file utils class or something, or file utils object. And it would download the content. And this is all synchronous programming. What that means is that the methods are called, the caller blocks while the callee does its thing. When the result comes back, you go on to the next step. Everything is synchronous, and you get a single value back, namely the array of bytes that correspond to that URL. So that's the old school way of doing things. By the way, it's still quite useful. I'm not denigrating it, just saying that that's the old way that started out back in early Java in the mid-90s. With 2014's release of Java 8, we got the first turn of the crank with modern Java, and that's the streams approach. And in this particular case, we've seen this example before. We're going to use something that's going to download a bunch of images that are not cached, apply filters to those images, and then collect the results into a list. And that is still synchronous. Even though it's running in parallel, it's still running synchronously. These are two-way blocking calls, just like they've always been, just like they were back in those days. In fact, we could probably use the download content method, or we do use the download content method to implement the download image method here. But in this case, we're getting back multiple values because we've got a stream of elements. So you can think of them logically as being like a stream of things where there's multiple elements in the stream. For example, we have a bunch of images that are turned into a stream of images, and then a stream of downloaded images, and then a stream of transformed and stored images, and then finally we collect that into a list. So we got multiple things going on in this particular case in parallel. So that's the parallel streams paradigm, which is synchronous multi-value. The next model is asynchronous single value. And this is what's supported with Java completable futures. So if you think about Java completable futures out of the box, here's a simple example we looked at a number of times. You get a big fraction. You are going to go ahead and reduce it in the background. And when it's done being reduced, you're going to convert the improper reduced fraction to a mixed string or a proper fraction. And then you're going to go ahead and print it out. Each of these completion stage methods that get called after the supply async factor method will return a single value, which will be completable future to something or other. Supply async returns a completable future to a big integer that's been reduced. Then apply returns a completable future to a string that's been converted to a mixed string or mixed fraction. And then accept then returns a completable future to void, just saying, I'm done. But we have single values for each of these things. So single value, yet the computations run asynchronously. The next way of thinking about things is asynchronous with multiple values. And we can get this with modern Java circa Java 8, 2014, by combining streams with completable futures, and more specifically with sequential streams with completable futures. And so you can see here what we're going to do is we're going to have a stream of URLs, and then we're going to run that through a bunch of intermediate operations, which are going to download them asynchronously and apply filters asynchronously and collect them and so on and so on and so forth. And so we end up with multiple values, but the computations themselves run asynchronously. So that's an example of asynchronous multi-valued approaches. And that's getting us closer to reactive programming. In fact, I think it's arguably reactive programming. However, it's kind of putting two things together that aren't quite designed to be reactive programming, although they're pretty darn close. So the fourth, or I guess it's really the fifth thing we're looking at here, is the reactive streams model itself. And in this case, we have asynchronous and multi-value, except this is baked into the abstractions. We're not combining two things together to get this paradigm. We're actually getting it from the paradigm itself. And so here's an example where we use the observable class from RxJava, and we say, take that list of URLs and make it into an observable, which is basically a stream, and then run everything in parallel on a particular scheduler, download and store the image, and then collect the results to a list. And when you're done, wait for everything to finish running. So we have a stream here. All the computations are running asynchronously, and it's baked straight into the model. So just an example of how we can go all the way to nirvana of reactive programming using asynchronous multi-valued approaches in the context of reactive streams. Now, I would be remiss if I didn't also mention that there's another paradigm that's coming up. It's finally here after a long wait, and that's the so-called structured concurrency approach that's available with modern Java, starting with Java 19. And they have support there now for this approach where you can have effectively you can use these lightweight tasks, or so-called virtual threads, and these virtual threads can run in the common fork join pool, and you can combine them together in a structured way in order to be able to start a bunch of operations that run asynchronously, and then you can kind of join them all together when they finish. And this is an approach that's very new to Java. It hasn't really been fully integrated yet into the modern IDEs, so I'm waiting for that, and then I will demonstrate how to use it. But it's a bit more structured than the asynchronous style approaches we see here. And so we'll talk about that if we have time, if the IDEs support it before the end of the class. I'll show you how to use Java's structured concurrency, which is part of something called the Project Loom effort. Let's wrap up this discussion by discussing the pros and cons of Java reactive streams platforms. So there's some benefits. One of the good things is that you can get concurrency with a minimum number of threads, or a minimal number of threads across a wide range of thread pools. That's all that's all very good. And this, of course, is also a benefit that you get with Java parallel streams and Java completable futures as well. So it's not unique to reactive streams, but it is a benefit relative to not having this feature. Another nice thing you can do is you can scale up performance with relatively few resources. And there's a nice article here that does some benchmarking and demonstrates that if you do the more traditional style of web programming, which used a pool of synchronous threads, this is the web MVC style approach that we've actually looked at before, you can end up with some bottlenecks as the number of users and the number of requests go up. Whereas if you do things using asynchronous programming with WebFlux, which is this reactive server-side computing model, you get much better scalability. And that's because you don't have a lot of threads running around, and you don't have a lot of blocking, and you use asynchrony, and it's just more scalable. So those are some good things you get from using reactive streams. Another nice property is you very rarely have to spawn your own threads, just about never. You very rarely have to use explicit synchronization unless you do things like the memoizer stuff we talked about before, where you explicitly want to use shared mutable state as some kind of optimization technique. And because of the fact that these things go away, various accidental and inherent complexities of concurrency and parallelism are dissolved. Now, again, this is not unique to reactive streams. We get some of these benefits also with parallel streams, and we also get these benefits with completable futures. But reactive streams kind of combines those things together in a nice way. However, there are some limitations, and one of the main issues is that it takes a while to get your head around the reactive streams programming paradigm. Now, the fact that you folks have had a chance to kind of learn incrementally what a stream was in a more civilized way with Java streams and parallel streams, and you've also had a chance to learn about completable futures, getting acclimated to using Java reactive streams is pretty straightforward. If you had to start from the traditional programming paradigm we talked about before of synchronous single-value objects, your grandparents' Java, then you would have a harder time making that leap because there's more of a learning curve. But I think we'll be able to do it now because you've already seen these concepts. However, the key thing to notice is that there's a learning curve. And therefore, if you are trying to solve relatively simple problems at relatively small scale, you may find out that the overhead of using reactive programming, and by overhead I don't mean performance, I mean the productivity overhead, is probably going to be higher than just doing things the old-fashioned way. And it's not until you get to a point where you have very large systems that have to scale and use hardware resources effectively, think like Netflix, for example, where you've got lots and lots of concurrent users banging away on lots and lots of servers, that it really makes sense to start doing some of this stuff. Now, again, once you learn it, it's not too hard, but there's a cost associated with learning things. So that's the end of our evaluation of Java programming paradigms. Very similar to our discussion about Java parallel streams and Java completable futures, where streams, parallel streams, are typically more productive from a human point of view, but maybe not quite as performant, whereas completable futures were more performant, but maybe not quite as productive. And so once you pop into the model, the programming abstractions of reactive streams, you hopefully get the best of both worlds where it's performant and productive. But it does take a while to kind of get your head around it because asynchrony requires a whole different thinking about patterns of programming that work effectively in that context.